Thank you very much for the opportunity to present on electromagnetic studies of the Lithosphere-Asthenosphere system. I'd like to briefly acknowledge the individuals listed here, whom I've worked with to various extents in the past few years. I'm drawing heavily on that work here. Here's a brief outline of what I'll be covering in this presentation. First, I'll briefly review the physical concepts behind electromagnetic imaging of the solid Earth. Then I'll discuss what our core observable, electrical conductivity, or inversely electrical resistivity, can tell us about the Lithosphere-Asthenosphere system. Then I'll move into a few case studies and conclude with some comments on future directions of research. In electromagnetic studies of the Lithosphere-Asthenosphere system, we rely on the physical principle of electromagnetic induction, in which a time-varying magnetic field will induce a transient electric field and electric currents within a conductor. And the Earth does in fact conduct electricity. It is not a particularly good conductor, but it nevertheless does conduct electricity. We are surrounded by natural time-varying magnetic fields, and we can use those fields as effectively a source to determine how the Earth conducts electricity internally. At variational periods of greater than 1 second, or frequencies less than 1 hertz, these naturally varying fields are generally due to processes operating in near-Earth space in the magnetosphere-ionosphere system. At variational periods of less than 1 second, or frequencies of greater than 1 hertz, the fields are due to lightning strikes and more atmospheric phenomenon. If we make a few simplifying but almost always valid assumptions about the nature and geometry of these natural magnetic source fields, then we end up with the magnetotelluric method, or MT for short. This method can be used at a wide range of spatial scales, from tens of meters depth down to the upper mantle, and it is the technique utilized by the vast majority of electromagnetic lithospheric imaging studies. The general idea is illustrated in this image in the upper right. External source currents in near-Earth space or the atmosphere generate the source magnetic fields that then induce electrical currents within the electrically conducting Earth. Note that these induced currents themselves will generate their own secondary internal magnetic fields as well. If we work through Maxwell's equations for electromagnetism with the nature and geometry of the source fields in mind, then we end up with these partial differential equations on the upper left that we have to solve for the fully three-dimensional MT problem. Note that these equations have been transformed into the frequency domain, with omega as the real angular frequency. In MT, we always work in the frequency domain for reasons that will at least partially become clear momentarily. Here, E is the harmonic electric field vector, H is the harmonic magnetic field vector, sigma is electrical conductivity, which is a function of spatial position, and I is the imaginary constant. Mu naught is the permeability of free space, and the magnetic permeability of almost all materials is the same as the permeability of free space. I want to highlight a few aspects of these equations that reveal some of the characteristics and limitations of the MT method. First, note that these are in fact diffusion equations. On the left-hand side, the curl operator is essentially a very complicated second derivative in space of either E or H. On the right-hand side, we have I omega times either E or H in the frequency domain. In the time domain, this maps back to a first derivative in time of either E or H. So we have a second derivative in space related to a first derivative in time. This is a diffusion equation. This is the first key point I want to make about these equations. With the MT method, and really electromagnetic induction methods in general, electromagnetic fields diffuse through the Earth. This is a key difference with many seismic techniques, which in contrast operate in the wave propagation regime. Because we are solving a diffusion equation here, we cannot resolve sharp boundaries. Instead, those boundaries tend to end up blurred in our inversions just due to the underlying physics of electromagnetic induction in the electrically conducting Earth. Back to these equations, the speed of electromagnetic diffusion is set by the term in the black box here. In the frequency domain, for a fixed angular frequency omega, it's a bit more intuitive to think about this term as setting an intrinsic spatial length scale for electromagnetic diffusion, essentially the characteristic length scale, or skin depth, over which these fields will propagate before being attenuated away at a given frequency. You can see this in the lower middle diagram here. The electrical currents and their associated electric fields, shown as red vectors going into the screen in the Earth here, attenuate with depth over some characteristic length scale due to this diffusion. Note that the term in the black box here includes sigma, the electrical conductivity of the Earth through which these fields are diffusing. For low conductivity Earth, or equivalently Earth that is highly resistive, the term in the black box will be small, which means that the fields will diffuse rapidly through the Earth over large length scales. And remember that in a traditional diffusion equation, for example the heat equation, the diffusion constant would actually be 1 over the quantity in the black box when it's next to the first derivative in time. Hence the small value giving rise to large length scales here. Now, in contrast, for high conductivity or equivalently low resistivity Earth, the fields will diffuse slowly through the Earth over comparatively short length scales. This is because high conductivity materials absorb and attenuate, or effectively just diffuse away, electromagnetic energy much more than low conductivity materials. This is one important aspect of the MT method. We are generally more sensitive to conductors than we are to resistors due to the tendency for conductive material to soak up electromagnetic energy. You can see that illustrated here in the lower right. This schematic diagram demonstrates currents getting concentrated into more conductive regions, reflecting the tendency for electromagnetic energy to be absorbed into these conductive domains. Because of this, we are very good at finding the tops of conductors, because the length scale of electromagnetic field propagation changes from large to short at the transition from resistive to conductive. So the fields sort of pile up at the contact and sort of give us higher sensitivity. However, in contrast, we are not very good at finding the bottoms of conductors. Again, the fields tend to be absorbed within the conductor, and the length scale of field propagation is expanding when you go from a conductive material into a resistive material. So that makes it hard for us to pin down that lower contact. You can think of this in terms of sensitivity again. Our fields are being stretched over a larger depth range and are therefore yielding aggregated information about that greater depth extent. In our inversions, this results in the bottom of conductive structures being smeared down vertically in depth. Now, this isn't to say that we are insensitive to resistive structures. As I will show you later in this presentation, we are at times highly sensitive to resistive structures. But in general, MT is very good at finding the tops of conductors. Now back to the term in the black box. Note that this also depends on angular frequency omega. The fields will diffuse farther into the Earth with a decreasing omega, or equivalently increasing variational period. So this is another important aspect of the MT method. We sense deeper into the Earth at longer periods or lower frequencies. And this is one of the reasons why we work in the frequency domain in MT, because frequency is a proxy for depth here. So together, our depth of investigation in the MT method, and really in any electromagnetic induction technique, depends on variational period and the conductivity of the Earth. Longer periods allow us to see deeper, so to study the Lithosphere-Asthenosphere boundary, we generally need data that extend to at least periods of 10,000 seconds. And fields are able to propagate deeper in higher resistivity Earth. For example, in cratonic regions, which are generally more resistive for reasons that I will discuss shortly, MT data are often able to sense much deeper than in active tectonic regions, which are comparatively much more conductive. These physical principles are demonstrated again here in this animation. Here I'm plotting the size of the E and H fields with respect to a normalized E field. Note that the fields diffuse down into the Earth and are attenuated over a certain length scale. Note that the length scale is shorter at a variational period of 100 seconds on the left, and longer at a variational period of 1,000 seconds on the right. In the lower panel, note the effects of the high conductivity 10 ohm meter layer. First, you can see that the fields attenuate significantly through this conductive layer compared to the other less conductive units in the hypothetical Earth here. This is most evident in looking at the dashed blue curve for the H field. You can see in the upper boundary of this conductive layer that the distribution of the magnetic field changes significantly, whereas the change is much more subtle at the lower boundary of this highly conductive layer. Again, this reflects the fact that we are more sensitive to the tops of conductors than we are to the bottoms of conductors. Finally, in comparing the top and bottom panels, note that the characteristics of the fields through the entire depth range, including importantly at the surface, depend on the conductive layering here. The presence of that 10 ohmmeter layer significantly changes what we see at the Earth's surface. So this is how MT works in practice. By looking at fields at the Earth's surface, we are able to learn something about electrical conductivity at depth. And so that's exactly what we do in practice. We go out, we measure the vector components of the electric and magnetic fields at the Earth's surface at a given location. We then look at the frequency domain relationships between these different field components, both the amplitude relationships and the phase relationships. Again, working under the MT method, we have made a few simplifying but almost always valid assumptions about the nature and characteristics of our external source magnetic fields. And that allows us to just look at the relationships between field components at a given location on the Earth's surface and effectively normalize out the source, so we don't have to worry about it. In MT, the main quantity of interest is the magnetotelluric impedance, often denoted Z, which is the frequency domain ratio between the local horizontal electric and magnetic fields. However, we can also look at the frequency domain relationships between other field components, for example, between the horizontal magnetic field components and the vertical magnetic field component. Then we take our field data that encapsulate the frequency domain relationships between these various field components at a series of locations across the Earth's surface, and we feed that into an inversion. We can then obtain three-dimensional images of solid Earth electrical conductivity, or inversely electrical resistivity. These are just mathematical inverses of each other, and I'm going to use these terms interchangeably throughout the rest of this presentation. I briefly want to discuss what electrical conductivity can generally tell us about the Earth before getting into specific conductivity mechanisms in the case studies. In the crust, igneous and metamorphic rocks are generally highly electrically resistive at typical crustal temperatures, whereas sedimentary rocks are often electrically conductive, largely due to constituent clay minerals, possible carbon content, and often fluid-filled porosity. Fluids, particularly saline brines, can be highly electrically conductive. In tectonically active settings, and especially in volcanic systems, MT is very useful in mapping the saline fluids that are associated with magmatism. Graphitic carbon and sulfide minerals are also highly electrically conductive, and MT is very good at mapping out those phases, particularly in metasedimentary horizons that contain significant quantities of graphite and sulfides. Looking at more the entire lithosphere here on the right, temperature does control electrical conductivity in silicate minerals, and at upper mantle temperatures we can begin to resolve the increase in conductivity. Mantle hydration can also affect the conductivity of the upper mantle in a way that we can resolve. And melt is also electrically conductive, with the exact conductivity values depending on the composition, temperature, and percentage of partial melt. And although not explicitly shown here, grain size also affects the conductivity of the upper mantle, although only when grain sizes become very small, much less than 1 millimeter. For this reason, mantle shear zones may be conductive due to significant grain diminution along such structures. So these are the general factors that we think about when interpreting electrical conductivity images for the Lithosphere-Asthenosphere system. For the rest of this presentation, I'm going to focus on MT imaging of the mantle lithosphere and asthenosphere. In these domains, the key factors that control conductivity are temperature, hydration, the presence, composition, percentage of partial melt, and to a lesser extent, grain size and modal mineralogy. This plot here demonstrates how electrical conductivity of the uppermost mantle varies as a function of temperature, based on empirical electrical conduction laws derived from extensive laboratory experiments. These gray curves here in the upper part of the plot show electrical conductivity as a function of temperature for dry mantle for several different mineral assemblages and different mixing laws. Because the upper mantle is generally composed of several different mineral phases that each have their own intrinsic electrical conductivity behavior, we have to utilize mixing laws to determine how the individual conduction laws average into a bulk conduction law. However, note here that the uncertainty in different mixing laws is often small, here yielding an uncertainty of about 60 degrees C when trying to interpret an observed resistivity in terms of temperature. Also note that the effect of different mantle modal mineralogies is very small. This is because all upper mantle volumetrically significant silicate minerals conduct electricity roughly the same way in this dry limit, so we are generally insensitive to the details of bulk mineralogy. It is worth noting this gray region in the plot, labeled Not Observed. This field highlights conductivity temperature combinations that are physically impossible to observe based on what we know about upper mantle electrical conductivity from extensive laboratory experiments. The dry mineral conduction laws form an upper bound on how resistive the upper mantle can be as a function of temperature. For example, taking the thermal Lithosphere-Asthenosphere boundary to be roughly the 1330 degrees C isotherm under the continents, these empirical laws limit the maximum resistivity that you could observe at the thermal LAB to be roughly 300 ohm meters. So the thermal LAB cannot be any more resistive than this. This dry limit is going to become important in one of the case studies that I'll be showing you later. Now, these dry mantle mineral conduction laws are well constrained and are well understood after decades of laboratory experiments. However, in contrast, the empirical laws that describe electrical conductivity in hydrated nominally anhydrous minerals are notably less well constrained and are not widely agreed upon across the community. These blue, yellow, and red lines in the plot here show different hydrated mantle mineral conduction laws for fixed 200 ppm water with different modal mineralogies and different mixing laws. You can see that there are big differences between these curves, and if you were to try to interpret an observed resistivity value of 100 ohm meters in terms of temperature at an assumed water content of 200 ppm, you would end up with an uncertainty of several hundred degrees C due to these empirical ambiguities. And the dominant factor driving the scatter in these curves is really the differences in lab results for the effects of water content on conductivity between different lab groups. Moving forward, reconciling these differences is one of the big areas of future research. I'll also note that there is substantial interest in using MT to determine upper mantle water content. For one thing, water content is an important factor in controlling mantle viscosity, so MT is perhaps the only geophysical technique that can provide insights into that important mantle property. Now I'm going to go through a few case studies to illustrate the insights that electrical conductivity can give us into the lithosphere-asthenosphere system. I'll discuss 3 case studies, all from the conterminous US, the region I'm most familiar with. I'll first show results from the tectonically active northwestern US in order to demonstrate general patterns we often see in electrical conductivity images. Then I'll show results from the stable US midcontinent to highlight characteristics of stable Precambrian continental lithosphere and to demonstrate some lingering questions regarding evolution of the continental lithosphere through time. Finally, I'll show results from the southeastern US. This region is now a passive margin, and the last tectonomagmatic event here happened with the opening of the Atlantic at about 200 MA. But there's a very surprising story here that demonstrates how MT and seismic results need to be tied together to understand the lithosphere-asthenosphere system. I'll briefly note that the map here shows the distribution of publicly available MT data across the conterminous US and adjacent Canada as of April 2021. The orange inverted triangles denote long period data that were collected as part of the EarthScope US Array project, and those data have been very beneficial in studying the lithosphere-asthenosphere system across the US. The three case studies I'm going to show you largely utilize these EarthScope US Array data. The blue inverted triangles denote long period data from the ongoing MT Array project, which aims to complete long period data coverage across the southern US. We're very fortunate here to have this really great MT dataset to study the continental lithosphere in the US. Similar national scale programs in China, Australia, Canada, and parts of Europe have provided similar long period data coverage. For the first case study, we'll look at the tectonically active northwestern US. And here I just want to highlight a few of the general characteristics of the lithosphere-asthenosphere system that we often observe in MT imaging. These figures here show cross-sections through a three-dimensional electrical conductivity model from work by Nasser McBell, Gary Egbert, and colleagues. In this cross-section, up on top, the dashed white line here shows the MOHO, and the black dashed line shows the inferred thermomechanical lithosphere-asthenosphere boundary. First, I'll highlight these blue domains here, which have high resistivity values in excess of 1,000 ohm meters. These are Archean cratonic blocks, the Wyoming craton and the Medicine Hat block. Their high resistivity values are due to cold internal temperatures and depleted refractory constituent mantle. And when I say depleted here, I specifically mean that melt depletion has removed all the water so that the constituent mantle is now essentially dry, or at least containing so little water that it can in bulk be characterized by the dry mantle mineral conduction laws that I showed you before. This is something that is observed globally in lithospheric MT imaging. Cratonic blocks are often highly resistive, at least where they have not been recently tectonized. I want to draw your attention to the low resistivity, or high conductivity region around the Moho beneath the Snake River Plain. The Snake River Plain, labeled as SRP here, is a region of recent quaternary volcanism, and the low resistivity values here of around 1 ohm meter are interpreted to be due to ponded melt and associated saline fluids within the crust. This is something that we often observe in tectonomagmatically active regions, high conductivity or equivalently low resistivity domains, due to the presence of fluid and melt. You'll also note the moderately resistive region just beneath the inferred LAB here. Here resistivity values are about 300 ohm meters. The entire region here, between the subducting Gorda plate and the Wyoming craton, has experienced magmatism in the last roughly 30 million years. The interpretation for these moderate resistivity values in the asthenosphere is that partial melting has removed all the water from the constituent mantle material. Water is incompatible during mantle melting, so the leftover depleted asthenospheric material here is consequently dried out and falling along those dry mantle mineral conduction law curves that I showed you before. I should also note that this moderately resistive asthenosphere likely does extend through the whole region here, including beneath the Snake River Plain. And we don't see the moderate resistivity values immediately beneath the Snake River Plain due to the downward bleeding of the high conductivity values from the lower crustal conductor, but a continuous moderately resistive asthenosphere here would likely still fit the data. Finally, I want to draw your attention to this feature here, labeled CB. This conductor falls along the Cheyenne Belt, which is a suture zone between the Archean Wyoming craton and younger juvenile Paleoproterozoic volcanic arc terrains to the southeast. In the crust, the high conductivity or low resistivity values of around 1 ohm meter can be tied to graphite and sulfide-bearing metasedimentary units that were trapped within the ancient subduction zone that closed during suturing. You'll notice, though, that relatively low resistivity values of 10 to 30 ohm meters extend through the entire lithospheric column. It's likely that this relatively high conductivity structure is due to grain diminution along the mantle shear zone that is the downward continuation of the crustal suture here. So these are generally some of the patterns that we often observe in lithospheric electrical images. High conductivity zones associated with active tectonomagmatism and high resistivity associated with older, stable lithosphere. This next case study is from the northern U.S. midcontinent, from work by Paul Bedrosian at the USGS. The map here shows a depth slice within the mantle lithosphere at a depth of 140 kilometers through a three-dimensional electrical conductivity model. Note the lateral variations in electrical conductivity across this region. Paul has extracted depth profiles here from the more conductive regions, labeled as cluster A, and from the more resistive regions, labeled as cluster B, in order to compare the inversion results to empirical electrical conduction laws that I showed you before. You can see here that at lower lithosphere depths of about 140 to 200 kilometers, the more conductive domains, set A, are generally consistent with a more hydrated mantle with 300 ppm water. The more resistive domains, set B, are generally consistent with a less hydrated mantle with about 40 ppm water. So the observations here provide evidence for laterally variable mantle hydration. However, the cause of this variable hydration is unclear. Here in the northern midcontinent, we're dealing with mantle lithosphere that was stabilized in the Archean and Paleoproterozoic, likely through melt depletion. So the interpretation is that the hydration here was the result of some sort of subsequent metasomatic event. but the cause and timing of that metasomatic event is unclear. Some portions of these conductive zones could potentially be linked to later Proterozoic or Phanerozoic events, but generally the origin of this sort of mantle hydration is still an outstanding question. Similar patterns are observed in Archean and early Proterozoic lithosphere globally, and I'd say generally the source of lithospheric hydration via metasomatic events is not well understood. With these conductivity depth profiles, I also want to note that they generally become more conductive than might be expected in the uppermost mantle, at depths of 50 to 100 kilometers. Note here how the extracted model curves bend away from the empirical conduction law curves. Again, this is a pattern that is often observed globally in lithospheric conductivity imaging studies, but I would argue that it's not clear whether this is a real feature required by the data. The characteristics of the submoho mantle lithosphere is also, in my opinion, another poorly understood aspect in lithospheric imaging studies. Finally, I'll note there are some xenolith and xenocrystal constraints on upper mantle properties in this region. The xenolith and xenocrystal localities are shown with these red dots on the map here, and where these fall over more conductive mantle, they generally support the presence of fertile, more hydrated mantle. However, again, the source of this refertilization is unclear. The final case study will be from the southeastern US, and this is in fact work that I did during my PhD with Gary Egbert at Oregon State University. When we started working with the Earthscope US array data from the southeastern US, we found this very surprising, highly resistive structure beneath the Piedmont and coastal plain physiographic provinces, the regions here in this map. You'll note that the resistivity values in this structure are exceptionally high. The scale bar here is different than in the previous case studies, so these blue values here are in excess of 10,000 ohmmeters. Now you'll remember that I mentioned that there's an upper limit on how resistive the mantle can be as a function of temperature, and this was reflected as that gray not observed region in the resistivity temperature plot that I showed you before, and that I'm also showing again here in the lower left. Because of this upper limit, these very high resistivity values here require cold temperatures of less than 1200 degrees C, extending very deep. From resolution tests, we constrained these high resistivity values to extend to at least 200 kilometers depth. So from our MT results here, we concluded that the thermal Lithosphere-Asthenosphere boundary, with a temperature of about 1330 degrees C, has to be at a depth of 200 kilometers or deeper. Our MT results then indicate that the lithosphere here is characterized by this big, thick, cold, coherent block that has existed at least for the last 200 million years, since the last major tectonomagmatic event along this now passive margin. But this conclusion seems to be in sharp contradiction with all the seismic imaging work that has been done in this region. The cross-section on the right here is just one example from surface wave tomography work by Laura Wagner and colleagues. But the general patterns are the same across many different surface wave and body wave imaging studies. They all seem to show a variable thickness high velocity lid that extends to depths of no more than 150 kilometers. And those observations have been used to argue for a thermal LAB at depths less than 150 kilometers, with a patchy thermal lithosphere having been eroded away along the passive margin here over the last 200 million years. So we were left with this seemingly contradictory pictures of the lithosphere here from seismic and MT imaging. We've been able to show, however, that the seismic results are in fact perfectly consistent with the thick, coherent thermal lithosphere that is required by the MT. The plots on the lower right here show you how we were able to reconcile these different geophysical results. These show resistivity versus shear velocity, with resistivity mapping directly to temperature. I'm doing this mapping assuming that we're operating in the dry limit, those dry mantle mineral conduction laws I showed you before, and we're ignoring the effects of different modal mineralogies and mixing laws. Remember that resistivity temperature plot again that I showed you before. It's showed here again on the left. The different mineralogies, different mixing laws, the effects of those are small compared to the influence of temperature on dry mantle mineral conduction. And because of how resistive we observe the lithosphere here to be, the dry assumption has to be valid. The red circles on these plots here shows the matchup between VS and resistivity between the MT and seismic results that I'm showing you here. So for these two geophysical images at the noted depths, I'm extracting resistivity VS pairs within the highly resistive structure, and the median of that distribution plots at the red dot, with the bars off this dot indicating the range of VS values. The dashed lines here show you the predicted VS versus temperature for purely anharmonic effects. And the solid blue line and the gray region in each of these plots show you the predictions when incorporating anelastic effects from two different models for anelasticity. As I'm sure many of you know, there are two sets of effects that control seismic observables. Anharmonicity takes into account the fact that mantle minerals have their own intrinsic elastic properties, but it ignores the fact that those minerals have finite grain boundaries. Anelasticity takes into account the fact that the grain boundaries themselves also have their own shear modulus that contributes to the bulk mantle elastic properties. So you can see here that the observed VS values do not match up with the anharmonic predictions at the cold temperatures we infer from the MT images. However, the MT and seismic observations together do make sense when comparing to anelastic predictions. When taking into account the anelastic controls on seismic observables, the apparently slow VS values make perfect sense at the cold temperatures required by the MT. I'm showing you this comparison for just one seismic image here, but we've done this for many different tomography models and the patterns hold. So the seismic results here aren't giving us direct insights into the depth extent of the lithosphere and the location of the thermal lithosphere-asthenosphere boundary. It's only when combining the seismic results with the MT results that we're able to really understand what the lithosphere-asthenosphere system looks like here. I briefly want to mention one other interesting aspect of this case study, and that is that we might be able to explain the observed mid-lithospheric discontinuities in the southeastern US under the thermal regime constrained by our MT data. The receiver function image here is from work by Emily Hopper and Karen Fisher, and looking east of the Appalachians along the Atlantic coast, we can see a negative velocity gradient at a depth of about 70 kilometers. One important aspect of our MT images for the southeastern US that I've glossed over so far is that our data require very high resistivity values here, but we can't actually constrain exactly how high those resistivity values need to be. We can establish a lower bound on resistivity, but we can't establish a solid upper bound. And this is essentially because of what I was describing to you at the beginning of this presentation. We're more sensitive to conductive structures because the energy is soaked up in there. But in contrast, the high resistivity values don't really diffuse away electromagnetic energy. So when high resistivity values become this high, more than 10,000 ohm meters, we can't really constrain exactly how resistive they need to be. What we're really sensitive to here is the depth to the conducting asthenosphere, that is the depth to the 300 ohm meter mantle material. What this means in practice is that we can impose a wide range of resistivity depth profiles within this structure, and the main constraint we need to honor from the data is the depth to the electrically conducting 300 ohm meter asthenosphere. So, because we can impose a range of resistivity depth profiles, that equivalently means we can impose a range of different lithospheric geotherms that all have the 1330 degree C isotherm at 200 kilometers depth, the depth at which we know we have to hit that 300 ohm meter material based on resolution tests. So the two lower sets of plots here, on the left and the right, show two possible geotherms that when we map to resistivity using a dry conduction law will still satisfy our MT data. These curves here on the left of each set show the predicted body wave VS and VP versus depth profiles for these geotherms. The dashed black lines are again the purely anharmonic predictions, and the solid green and black lines are again anelastic predictions from two different models for anelasticity. The gray lines in the background here show you the AK-135 reference model with plus or minus 2% bounds. First of all, you can see that with both geotherms at depths of greater than about 140 kilometers, The anelastic predictions for body wave VP-VS are in fact slow with respect to AK-135, which matches observations from body wave tomography studies. More importantly, with the anelastic model of Corrado, Olegboji, and Park, which is shown on the solid black line, you'll see big predicted negative velocity gradients here that could give you mid-lithospheric discontinuities in converted wave imaging. Particularly with the geotherm on the right, we can get that MLD at a depth comparable to what is actually observed, about 70 kilometers here. So, under the thermal mechanical constraints from our MT data, we can explain multiple sets of seismic observables, including potentially observations of MLDs here. So I'll now wrap up this presentation with just a few notes on outstanding questions within electromagnetic studies of the lithosphere-asthenosphere system, and some thoughts on directions for future research. As a disclaimer, these of course just reflect my opinions, but I do think these are avenues that the greater EM community is moving down in current research. First, as I discussed a bit in the case study from the US Midcontinent, a major area of ongoing and future inquiry is what MT data have to say about upper mantle hydration, particularly regarding vertical as well as lateral variations in lithospheric hydration. And the question of what causes this lithospheric hydration is, to me, a big topic for future research. And I'll of course note that the big spread in lab results for the effects of mantle hydration on conductivity pose a problem for us in interpretation. So hopefully future lab work will be able to reconcile all these differences. Another big push forward is in trying to tie mantle xenolith petrology to MT observations. And here I'm particularly talking about more unusual lithologies like pyroxenite veins and phlogopite-bearing lithologies. I think the MT community in general has been doing a good job at tying our results to bulk xenolith observations, and good examples are found in the work of Alan Jones and Javier Falea. But I think a big lingering question is how these more unique compositions, particularly phlogopite-bearing xenoliths, bear on our MT observations, since in the case of phlogopite, it can be very electrically conductive at mantle temperatures. Kate Selway and Sinan Ozaiden at Macquarie University have been doing some really interesting work recently to consider how these unique mantle lithologies that maybe only represent small, localized pockets of the mantle lithosphere bear on MT observations that intrinsically integrate information over large swaths of the lithosphere. Finally, and this is something that we as solid Earth geophysicists always are, or at least always should be trying to do, we really have to combine multiple geophysical pictures in order to really understand the lithosphere-asthenosphere system, as I demonstrated with that last case study from the southeastern US. Continuing to integrate geophysical approaches into united concerted efforts is really, I think, how we'll make progress in understanding the lithosphere-asthenosphere system in the future. And I'll note that new software tools, and not just 3D inversion codes, but also new tools to aid in interpretation and integration with other datasets, will really help in pursuing these future research subjects. If you'd like to learn more about electromagnetic studies of the lithosphere-asthenosphere system, I'd encourage you to check out this review paper that several colleagues and I published earlier this year in Physics of the Earth and Planetary Interiors. It provides a good introduction to thinking about how we use MT to study the lithosphere-asthenosphere system, and expands greatly upon the many ideas I've presented here. Thank you very much for your attention.